Welcome back to the Centra seminar, everybody. This week we have Valentin Boyanov, who is going to tell us about the black hole inner horizon instability in classical and semi-classical gravity. Valentin, the stage is yours.
Thank you, David. Yes, so I will talk about instability, black hole inner horizons, in both classical and semi-classical gravity. This is a work I've done as part of my PhD thesis under the supervision of Carlos Barceló, Raúl Carballo Rubio, and Luis Garay in Madrid. And I just finished 2 months ago. So this is part of my thesis defense presentation with some parts amplified, well, extended, so that hopefully it makes for a good seminar. So to set the stage a bit, let me first remind you that thus far, the two most successful results of mixing quantum and gravitational notions are, on the one hand, the perturbations in the early universe, as described by fluctuations of quantum fields amplified during inflation. And on the other hand, the evaporation of black holes through the emission of Cauchy radiation. And both these results are within the framework of quantum field theory in curved spacetimes, which I will also use here. Now, when it comes to black holes in particular, this framework is far from exhausting its full applicability. In particular, analysis regarding the interior of black holes in the region of the inner horizon are not yet complete. Now, inner horizons of black holes are known to be unstable, on the one hand, classically, due to the mass inflation instability, whereby if you perturb a black hole with the inner horizon, some generic perturbations expected to be present in space-time after gravitational collapse, then the inner horizon destabilizes and curvature begins to grow very rapidly in this region. On the other hand, there's also a semi-classical instability, which is known, where if the inner horizon is long enough for the Cauchy horizon to form, then the vacuum energy of quantum fields tends to a divergence in the vicinity of the Cauchy horizon. And here I will, the aim of this talk is to review and re-examine both backreaction from both these effects, first separately, and then I will make some preliminary results regarding how they might act jointly in strictly symmetric spacetimes. So I think I skipped, yes. So let me start with the classical part. So classical gravity, as probably all know, is governed by the Einstein equations. Where on the left-hand side you have the Einstein tensor, on the right side you have the stress energy tensor of matter, which, being classical gravity, is generally considered to satisfy certain energy positivity conditions, which not only affect how the matter itself moves, but also how space-time is allowed to evolve. And within this theory, black holes are a solution which is obtained from generic initial data. Now, when one thinks of the formation of a black hole, the picture that usually comes to mind is something like this. You have a distribution of matter which is collapsing, and at some point it becomes dense enough where a trough region forms, and then it continues to collapse inside the trough region until eventually it reaches infinite density and a singularity is formed. Now, if you're only worried about what happens as seen from the outside of the black hole, this picture is usually sufficient, but if you're interested in studying the interior of the black hole, then you have to keep in mind that the picture for generic black holes is a bit more complicated. What usually happens is that a trough region begins to form at some finite radius inside the collapsing matter distribution. And then from there, the outer horizon begins to move outward as more matter is accreted. It can only move outward classically. The matter content satisfies energy positivity conditions. And it eventually just stabilizes at some finite radius when all the matter is accreted. And the inner horizon, on the other hand, the lower boundary of the trough region, begins to move inwards. It's classically only allowed to move inwards. And it either goes directly to the origin, if, for example, Schwarzschild black hole forms, and then a singularity response, space-time singularity, or if the matter distribution is collapsing, it has any electric charge or any momentum, then the inner horizon tends to stay at a finite radius. And as to what happens to the actual collapsing matter, particularly in the case of resonant motion, there's some solutions that show that because of the electric repulsion, it actually tends to stay around the inner horizon. And part of it actually crosses the Cauchy horizon, this inner horizon forms. So, yes, this doesn't really work. So, what happens with long-lived inner horizons is that, well, trajectories tend to be accumulated, geodesics tend to be accumulated around it, particularly ones which try to escape the interior of the black hole. And for these geodesics, the proper time, or time parameter generally, for geodesics as well, tends to slow down a lot with respect to the time seen by, well, measured by observers outside the black hole. So much so that the entire lifetime of the external universe can pass, but for these geodesics which approach the inner horizon, only a finite proper time passes. And this is going to this relation here, where this is the time parameter, and V is the angle of the sine ingoing coordinate, which is proportional to the proper time distant observers, and capital I is the surface gravity of the inner horizon. So V goes to infinity, but C only goes to a finite value. And this leads to the generation of a so-called Cauchy horizon, beyond which these geodesics which approach the inner horizon can be extended, and the geometry itself can be extended, but the evolution of the geometry is no longer determined exclusively by initial data at the past Cauchy surface, hence the name Cauchy horizon. So what happens around Cauchy horizons, one of their main property is the fact that due to this discrepancy between the time that passes as you approach the Cauchy horizon and the time in the external universe, perturbations tend to be blue-shifted around it. This can be visualized easily. For example, you'd say a series of equally spaced in time signals, and you send them into the black hole. From the external universe, they can be equally spaced, but for an observer which approaches the Cauchy horizon, they will tend to get bunched up to the point where, when you cross the Cauchy horizon itself, you get hit with infinite density. Now, generally, what this means for actual perturbations, which are expected to be present in generic black holes, is that if the perturbation doesn't decay as quickly as this exponential here, the same we had for the proper time relation before, if perturbations decay more slowly than this in following perturbations, then you get this infinitely bunched up signal at the Cauchy horizon itself. And as it turns out, generic perturbations on black holes do indeed decay more slowly than this exponential here. For asymptotically flat spacetimes, they're expected to decay as an inverse polynomial of the time external to the black hole, which is usually known as Price's law. And for asymptotically simple spacetimes, they're expected to decay as this decreasing exponential here, where capital C is the surface gravity of the cosmological horizon, which is much smaller than the surface gravity of the inner horizon due to the scales involved, at least in our universe. And so, indeed, perturbations decay more slowly than this, and they're amplified at the Cauchy horizon until a divergence is reached. For anti de Sitter, I believe that the perturbations also decay exponentially, though maybe a bit more quickly. So, yeah, I'm not sure. For anti de Sitter, yeah, I think there it would depend a bit on the actual scale, the anti de Sitter scale. Once again, if the anti de Sitter scale is much smaller than the cosmological constant is much smaller than the surface gravity scale of the inner horizon, then maybe it's it's the same picture, but the ADS curve is quite bigger than might be different. Yes.
So the decay exponential is kinetic decision, the decay exponential is very specific.
Yes.
When you move away from shared vicinity, it becomes
Logarithmic. Okay, so yeah, logarithmically would definitely trigger it. Thanks. So yes, this is what is the triggering point of mass inflation. And to understand what actually happens to the geometry during mass inflation, let's look at a simple model in which we model the infalling perturbation by a series of discretized perturbations in the form of no shells which collapse and increase the black hole mass by certain amounts. The amount of the quantity of these masses we impose has to decay as either this inverse polynomial process or this inverse exponential corresponding to the cosmological case. And we consider that the black hole between these perturbations is static. Static patches separated by these shells. And we also place an outgoing shell, which is there to model the backscattered part of the flux, which is inside the trapped region, which is also essential to study backreaction in mass inflation. So with just these shells and static patches of spacetime, with the junction conditions at the intersection points of the shells, which are required for the metric to be continuous, we can solve, well, and also imposing what the masses of shells are initially, we can solve the evolution of the geometry and see the mass inflation effect. So the junction conditions give us that basically the redshift function in this region here, so the function PT component of the geometry we saw before, in this region here, evaluated at this point Q, the intersection point, tends to increase exponentially. It's an exponential that grows in between each of these intervals, again governed by the surface gravity of the inner horizon for each of these sections. And well, this increase in the redshift function is proportional to an increase in curvature and mass. And so it's not suppressed by the terms which multiply it, then mass inflation takes place. And well, the terms which multiply it, one to look out for is this difference between the inner horizon position in the regions C and B. And if that is smaller than this growing exponential asymptotically for these subsequent perturbations, then you get mass inflation. And indeed, it is smaller for cases of rising nostrum, similarly for pair, although it's significant. And yeah, they actually tend to decay the same way that we impose the mass infalling perturbations. And so this condition is satisfied, usually, although you might imagine some particular black hole models in which the inner horizon resists a bit more to deformations from mass perturbations. And this quantity is actually a bit, yes, it actually manages to suppress the exponential. And in those cases, you would maybe not get mass inflation, but generically it is expected to take place. And so what happens when it does take place is that the Misner-Sharp mass in the region below the outgoing shell, so in these regions A, B, and subsequent ones, tends to grow exponentially, so does curvature. And as a consequence, the position of the inner apparent horizon tends towards the origin as this became exponential averaged out of the discretized patches. What the geometry looks like in this interior mass inflated region is something like this. We have this line element here, where we have the radial temporal part with a redshift function, which has a mass term which grows exponentially. But this whole part is also multiplied by this function A, which we call the freezing function. It's a decaying exponential in time. And we call it a freezing function because it acts to freeze the descent of geodesics inside trapped regions. So usually inside the trapped region, even the outgoing geodesics would tend towards the inner horizon. But because of this function here, many of them tend to freeze in their descent and actually tend toward finite radii. And what this does is that instead of going to the inner horizon, which itself is approaching the origin and the formation of a strong curvature singularity, they instead are left inside the trapped region and approach towards a weak curvature singularity. And in this case, weak singularity I take to means one for which there is a divergence in curvature, but the overall tidal deformation of objects which cross it is finite and the metric is extendable beyond it. And so you get both, because the inner horizon goes to the origin, you get a strong curvature singularity where a metric is not extendable. But you also get a weak singularity toward which these frozen geodesics go. And space-time is actually continuously extendable past the weak singularity. And if the inner horizon goes to the origin in a finite time, as seen from the outside, then the strong singularity is space-time. Whereas if it takes an infinite time, as seen from the external universe, then the strong singularity will also have a null component. Okay, so this is it for the classical part. There are any questions about it? Now is a good time. And if not, let's. Oh, yes.
When you said that seen from the outside of the black hole, so it says vaporizing.
Well, yeah, I mean extending the time coordinate to the external universe to the inside. Not really anything seen yet.
Constant time.
Yes. So basically the V coordinate you can use as a good measure of time. Yes.
Picture here showed what's it look like the outer horizon would grow.
The outer horizon would grow. Yes, because the shells are falling, then falling shells. Then the mass of the black hole as seen from the outside does tend to increase slightly, and the size of the black hole increases slightly as this decaying, well, corresponding to what the decay of the perturbation we've imposed is. So it would increase, but slightly, as seen from the outside. But the mass that increases on the inside is a local definition of mass. So that effect isn't seen from the outside.
When you say here that in the weak singularity case that it's you can have a continuously extendable metric, is that as regular as it can be?
You mean whether it can actually be smooth?
Yeah, well, could it actually be a solution?
Well, as far as I know, what's shown is that generically for this type of singularity, it's only C0 extendable metric.
Yeah.
So not anything more than that. So you can call it weak solution or something. I'm not sure what the terminology is. But yeah, it is technically considered to be still a viable Cauchy horizon in the sense that, well, it's a problem for cosmic censorship and things like that. Okay. So there are no more questions for this part. Let's move on to the semiclassical part. So semiclassical gravity, much like classical gravity, is described by the Einstein equations. But in this case, on the right-hand side, apart from the stress energy tensor of the effectively classical microscopic matter, we also have this quantity here, which we call the renormalized stress energy tensor, which is the renormalized vacuum expectation value of an operator constructed from quantum fields and their derivatives reside in space-time. And it's ultimately a function of the geometry once you calculate it. So for practical purposes, you can see this as the modified theory of gravity, but one with a very clear principal motivation behind it. And generally, the renormalized stress energy tensor is suppressed by a Planck scale. So in practice, it's the effectively classical matter which generates the bulk of background spacetimes, while the renormalized stress energy tensor just acts as a perturbation. But some particular geometries do have important semiclassical corrections, aside from ones in which curvature becomes Planckian and the Planck scale suppression is overcome in that way. The renormalized stress energy tensor can also have important corrections when to the spacetime when trapped regions are involved, particularly at the outer and inner parent horizons, trapped regions. Important semiclassical effects can take place due to the causal properties of these horizons. So calculating the renormalized stress energy tensor involves complicated regularization and renormalization procedure. And ideally, we would want to do this for all the fields of the standard model of particle physics, so quantizing the full interacting theory on an arbitrary curved space-time background. But considering that this is difficult, not directly impossible with current techniques, what is usually resorted to is using guest fields. In this case, I'll use a massive scalar, minimally coupled to gravity, and sufficiently simple space-time backgrounds. In this case, in spherical symmetry. But even in spherical symmetry, when spacetimes are dynamical, we have to resort to further simplifications. And what I'll use for the renormalized stress energy tensor calculations is what's known as the Polyakov approximation, in which one quantizes a field in a 1 + 1 dimensional geometry corresponding to the radial temporal sector of the 3 + 1 geometry. And then using the result from there to define the normalized stress energy tensor in 3 + 1 dimensions. Now, this is an approximation, and we don't have a precise control of how exactly it is, but we do have some observations. Particularly, we see that it seems to work really well around horizons. It captures the Hawking effect for one thing. It also gives the expected divergence at the outer horizon of black holes that we do with all our quantization. And also it gives the correct divergence at the Cauchy horizon for the Unger state and other physical states, which we'll talk about more in a bit. But of course, there are some problems to its use. It's essentially like an S-wave approximation, which also ignores backscattering. So there's some effects that it doesn't capture. And it also has a non-physical divergence at the origin, which, well, we have to be careful with. It's typical of S-wave approximations. So we have to make sure that we're sufficiently far from the origin in terms of the Planck plane, so that the results are a bit more trustworthy. And one final comment on the methodology. Proceed with the results. Quantization in curved spacetimes usually has an ambiguity related to it, which is basically due to the fact that there's no preferred choice of basis of solutions of the quantum fields, the field equation, which define particle states. So you need to choose a basis of solutions for defining particle states, but well, in flat spacetimes, you take the plane wave basis and you get a quantization that satisfies the symmetries of flat spacetime, and that works really well. But in curved spacetimes, where you have less symmetry, there's generally no one unique preferred way to do the quantization. But in isolated gravitational systems, we can work around this ambiguity by defining the asymptotically flat region in the past, the Minkowski-like quantization, taking the plane waves as our basis for the field solution, defining the particle states, and then propagating these solutions forward through the region of curvature. And this is what defines the so-called thin vector state, which is the standard choice of black hole studies, gravitational collapse in general. So let's quickly look at how these tools can be applied to recover the result of Hawking evaporation before we. Yes.
We have inside before, then inside Polyakov.
Yes. This one.
Some angular excitation.
Yes.
So we make some direct.
Yes. So it's essentially only considering the radial part, field equation, and also a radial. Yes, you ignore the angular balance. So, for example, if you had any effects related to light rings, the potential circular motion, geodesics. When, yeah, for example, maybe studying effects, there's some suggestions that, for example, light rings would have, particularly not our light rings, but thinner light rings, would have very low microplates. They are known to be unstable classically, and maybe they have some semiclassical stability as well. But this approximation wouldn't capture that because, well, it ignores that part of the field propagation. Okay. So, talking about evaporation. Let's take the formation Schwarzschild black hole, the simplest formation model in which the black hole is formed by collapsing no shell. Before the shell, we have flat spacetime, and in the future, we have a Schwarzschild black hole. This isn't the most physical representation of gravitational collapse, but it serves to simplify the initial conditions of the modes of the quantum field as they have to black hole region. And essentially, for the in-vacuum state, I mean, the Polyakov approximation, what we need in order to calculate the normalized stress energy tensor is basically to solve just the radial non-geodesics in the space-time. And the feature which is important around the outer horizon is this peeling of the outgoing geodesics off of it. So this way in which finite interval, so the light rays in a finite time interval here end up filling the whole exterior of the black hole as more time progresses, they get peeled off, so to speak. That's the usual terminology. And what this does to the normalized stress energy tensor is that it produces this negative angle flux at the outer horizon, which depends on the surface gravity of the outer horizon, its capacity pole, and also depends on what it's suppressed by the Planck scale. This is the Planck square here. It also depends on the horizon position. Now, using this flux and the rest of the normalized stress energy tensor as a source of perturbation, we can look at the tendency that is, well, the effect it has to have on the geometry by taking the perturbation of the geometry and sourcing it by this tensor. We can look at the way in which it tends to modify, in particular, the position of the outer horizon, and we see that it tends to push the outer horizon inwards. So this is to be expected because this flux is negative, so it violates energy positivity conditions and leads to a classically forbidden evolution of the horizon, where it goes inwards instead of the standard classical picture in which the black hole can only grow. Now, because it goes inwards and it does so very slowly, because there is suppression by the Planck scale here, we can take a quasi-stationary approximation and actually solve the backreaction problem more precisely Now what we find when we do this is that the evolution of the outer horizon depends on, well, goes as this cube rule time, once again with the Planck scale expression. And what this gives us is that the time it takes the outer horizon to reach the origin, the black hole to fully evaporate, is standard Cauchy evaporation time, which depends, well, goes as with the cube of the mass of the black hole, the initial mass. And for a solar mass object, it's very, very long. So it's 10 to the 73 seconds. It's much longer than the current age of the universe. Okay.
So when you say solve the backreaction, what exactly are you doing?
So what we're doing is assuming that, well, perturbing the geometry and taking a source term to be the normalized stress energy tensor, and also with the assumption that the evolution is sufficiently slow.
Just the TBV or you have everything?
There's other terms as well, yes. I haven't shown here, because the TVV is basically the one that drives the evaporation. But yes, there are, in the Polyakov approximation, there's no angular terms, because, but there is a radial term as well. And, but yes, it takes the full tensor into account.
If you feed it back to the geometry, then
Yes.
what?
And then you solve a perturbation of the geometry. And yes, basically you see that the evolution, well, yes, if you also make the hypothesis that the evolution is sufficiently slow, then you can sort of iterate this process of, well, you can basically assume that the source has the same dependence in the scales of the geometry, say the surface gravity and radial position of the horizon, that it does when the black hole is static. And so that simplifies the source term. And then you can solve the full equations by basically putting a source term which has this exact form, but with the dynamic surface gravity and the radial position of the horizon. And so you take this source and you get the solution. That's the difference with this initial perturbed result that only takes into account the initial values, the surface gravity. The full dynamical one takes into account their time variation as well. This is the quasi-stationary approximation that is typically used for calculation. Okay. Any other questions on this part?
Usually evaporate quicker than force. As it evaporates,
Yes. As the surface gravity grows, it will tend to evaporate more quickly. And toward the end, what you're doing is essentially an extrapolation of the initial tendency. But yes, up until the surface gravity gets close to the Planck scale, then it's more or less correct. It has also been looked at numerically, and it reproduces the same behavior. Okay, so in this picture, the result is that, well, the outer horizon shrinks following a final surface until it reaches the origin. But this picture, which of semiclassical black hole evolution, which only takes into account backreaction around the outer horizon, leads to a somewhat incomplete picture. There's the issues, well, on the one hand, there's of course the issue of information loss because of the presence of the singularity. There's also, if you take this picture at face value, there's a failure of predictability at this point where the outer horizon means singularity. But what's more crucial for the purposes of this work is the fact that it doesn't take into account the complete classical description of the background black hole, particularly ignoring the inner horizon and its dynamics and potential backreaction around that. So going back to inner horizons, there have been some works few and far in between, but there have been works which look at semiclassical effects around the inner horizon, but only in cases in which the inner horizon directly coincides with the Cauchy horizon of maximally extended geometry. So in cases of spacetime like this, from this classic paper by Byron Davis from 1978, what they look at is the renormalized stress energy tensor in the vicinity of the Cauchy horizon, not in another form in the horizon. And what they find is that the renormalized stress energy tensor diverges at the Cauchy horizon, which is not really surprising considering that the blueshift, which affects classical perturbations, also acts on the modes of the quantum field and blueshifts them, and this results in divergent vacuum energy density. However, one wants to obtain a full picture of what black hole evolution looks like. You have to keep everything in mind. In this case, for instance, the fact that the trap regions only have a finite lifetime, long finite, if you take into account Hawking evaporation. And so the approach toward the Cauchy horizon is never really completed, physical standpoint. But these works do provide some important insights as to what the magnitude of the renormalized stress energy tensor is around the inner horizon asymptotically. The inner horizon is long and lived enough for the Cauchy horizon to be approached. And what they estimate is that back reaction from such a tensor would be much stronger than classical mass inflation singularity. And so it's very suggestive that if we take back reaction problem of the inner horizon at finite times, then there might be some significant deviations from classical evolution. So let's look at it. Let's construct a black hole. In this case, instead of it being a standard partial black hole, only an outer horizon, and show coinciding with the inner horizon until the singularity is formed. Let's take a long-lived inner horizon, which initially is at some constant radius. And let's look at the renormalized stress energy tensor in the vicinity of the inner horizon. Now, once again, the calculation is just related to the behavior of geodesics around this horizon. And because the behavior of the geodesics is essentially the same at both horizons, but one is the time reverse of the other, here you get a feeling of the geodesics of the horizon. And here you get the time reverse of that, which is accumulation of geodesics toward the horizon. What this ends up doing is giving you pretty much the same term as you had in the other horizon. But in this case, it depends on the surface gravity of the inner horizon. Its radial position. That's once again a negative in flux. Now, if we do the same and just look at what back reaction tends to do initially to functions of the geometry, what this effect has on the radial position of the inner horizon, we see that there's an initial tendency for the inner horizon to move outwards. So once again, a classically forbidden motion, because the source term is violating energy conditions. And so the trap region actually tends to slowly shrink from the inside the inner horizon approaching the outer one. I say slowly, but actually the initial tendency is exponential in time. So what this means is that what's suggestive of the general instability of the inner horizon also take effect in this case and make the dynamics much more rapid. But it also means that we can't really apply a quasi-stationary approximation like we did in the Hawking calculation, and we can't obtain a full solution easily. If we extrapolate, let's assume that the exponential tendency continues, then which is somewhat justified by the fact, by the observation of how the classical instability behaves, and by the fact that the flux which sources this initial backreaction is expected to continue to be present, then we can estimate the time it would take if the exponential tendency continues for the black hole to fully disappear by the inner horizon reaching the outer one. And it would take a very short time for a solar mass object, take the order of 10 to the minus 4 seconds. First, because the behavior is exponential, but this is of course an extrapolation. It's not a precise exact solution, and it's also ignores the fact that the background inner horizon is actually undergoing mass inflation. So if we actually try to take into account mass inflation, things get even more complicated, because now you have an inner horizon which which has dynamics as well in the background. And so we can approximately calculate for instance, this kind of space-time, or what's this conditions with flat region. And then we move on to a black hole region, which is immediately undergoing mass inflation. But we can only calculate precisely analytically the normalized stress energy tensor in a small vicinity where the inner horizon begins its timeline trajectory. And while we see that it does tend to perturbatively slow down the descent of the inner horizon, we can't really say whether it ends up dominating or not, except in some very simple geometries. So if we consider that, well, we have this line element here, which is the mass inflation geometry we saw earlier. And if we consider that the redshift function is such that it reproduces the causal behavior of mass inflation geometry, but in a small but finite interval around radial interval around the inner horizon, it only depends linearly on the radial coordinate, so just a geometric model. Then we can actually solve, if we consider this as a classical background, we can solve the semi-classical equations a bit more precisely for a small but finite time interval. We once again get a source which is out of the parts of the normalized stress energy tensor. It's once again a negatively moving flux. And the evolution of the inner horizon we obtain for these simple geometries is, well, first we have the classical tendency of the inner horizon toward the origin, as this decaying exponential, we saw in mass inflation before. But we have a correction which is suppressed by a Planck constant, but tends to grow exponentially. So the Planck scale suppression is overcome very quickly. The approximation is used to obtain a solution, break down when this correction term becomes at the order of the background. So in this picture here, it will be about until about the point at which the inner horizon stops its descent. But once again, if we extrapolate and take this initial result as it is, then it seems to suggest that the tendency with which the dynamics continue is for the inner horizon to begin moving outwards. And this is what we call potential semi-classical inner horizon inflation, which acts in the reverse way compared to classical mass inflation, pushing the inner horizon outwards. So to conclude, the natural time scale of black hole evaporation from the outside is the Cauchy evaporation time, which is famously very long. But if we consider generic black holes, which also have an inner horizon, then there is an additional time scale which enters into the problem, and it seems to be much shorter than the Cauchy evaporation time due to the intrinsically unstable nature of the inner horizon. And well, our preliminary results seem to show that semi-classical correction has the potential to overcome the classical dynamics of the inner horizon and push it outwards. But this is only very preliminary results, and the full evolution of the cap region is still an open problem. Ignore the last point. It's left over from my thesis defense, where I looked at warp drive spacetimes as well. In case anyone's interested, you can ask me, but ignore that for now. So the possible outcomes of the semi-classical evolution black holes with these conclusions in mind? Well, there's three possibilities essentially. First, while it's contrary to the initial tendencies observed, it's still possible that the initial tendencies are only initial, and that overall what ends up dominating on longer time scales is just the pulp and evaporation of the outer price. Nothing from the inside actually manages to get out. The other possibilities, which are more in tune with the results, are that, well, the inner horizon moves outward, and on the one hand, either meets the outer horizon and ends up forming an extremal black hole, which is long-lived, potentially semi-classically stable, or it moves out, the inner horizon moves out to the point where the trapped region disappears completely. And, well, a full numerical evolution of the equations is still necessary to discern which is the actual outcome, and it's something we're very much working on right now. But important thing to keep in mind is that if the trapped region does disappear completely, then very compact, dark physical objects which are observed would have to be horizonless black hole emitters, which, by the way, also happen to be solutions of the semi-classical equations. But that's another topic for another time. That's all. Thank you.
Oh, thank you for your very nice and very clear talk. Do we have any more questions?
Going back to the picture of the bounce,
Yes.
what exactly do you calculate here, and what exactly do you expect?
So what we take is a geometry of this type in the vicinity around the horizon, where the function, well, A decays exponentially, and this makes the causal structure like a classical mass inflation background, where the inner horizon tends toward the origin. And what's important for semi-classical corrections is essentially the behavior of the causal structure, which governs the behavior of no geodesics around the horizon. And so we take the simplest possible background, and assume that this is what the geometry looks like around the inner horizon, initially classically. And then we calculate the renormalized stress energy tensor on this background, and then we perturb the background and see that actually the perturbation with this source becomes, well, can be solved for a finite time interval, because with the perturbation taken into account in the calculation of the normalized stress energy tensor, you see that the perturbation is secondary to this initial term until essentially these two terms in the expansion become of the same order, and so the source term can continue to be calculated throughout it, just with the classical background.
Do you get this feature? Do you get these starvings? Complete on the
Only up until here is where the solution is the approximation and balance. And from this point on, it's an extrapolation. But I mean, the initial tendencies suggest something like that, so we like the pictures which include the extrapolation.
Charlie?
On the slide where the inner horizon becomes smaller and then it turns
Mhm.
bigger. Is there anything, is there like a characteristic time scale where it's changes? Like, you know about it.
Yes, it's essentially the same exponential that we had in the classically static case, so it would be the same time scale that I talked about very short. I think the exponential tendency actually continues beyond where our approximation breaks down. Yes.
So the final black hole doesn't go to zero. So how does this relate to the previous? Because this is essentially the same model, but you had a charge, but the exterior is essentially the same. The shells. So in the other case, we have the upper horizon going to zero. So it's completely.
The outer horizon.
the radius of the upper horizon. The first example is we talked about Hawking evaporation.
Yes.
And the radius would shrink to something.
Yes. But that
Here
takes
it doesn't go to 2.
a very long time. So here we're neglecting it because the time scales are very different. The Hawking evaporation time is of the order of 10 to the 70 something seconds for a solar mass object, while this is of the order of 10 to the -4. This part of the evolution is the results of
All
this.
of it will just be the final explanation.
Well, it's essentially the time it takes for this exponential form of the part scale suppression, so the scale is the same.
So the whole evaporation is going to be a failure.
If the initial trend continues, then yes, it would be very quick. Essentially, it would mean that trapped regions are unstable, and as soon as the trapped region forms, it disappears. Because it's, of course, we don't know whether it actually happens. Yes. And if it does, well, as I said in the final sites, then the dark compact objects which are observed would have to be something without trapped regions, which, well, is a proposal that's gaining popularity in recent years.
Any more?
It is known that vertically charged black hole charges very quickly because black hole polarization will tend to attract
Yes.
particles with different charge.
Yes.
And I think this is much quicker than
Yes.
those timescales that you are involved. So that picture will not happen. Because you'll get that, you get essentially a Schwarzschild black hole very quickly.
You say that the discharge scale is much quicker than this scale here.
I think so.
Of the order of 10 to the -4 seconds. So
Maybe not.
I think it's a bit longer than that because it's governed by Hawking evaporation essentially. So it's the time it takes for Hawking particles to take the charge away. And it's related, it's shorter, much shorter than the Hawking time, but much longer than this inner horizon effect time. And that's why it wouldn't noticeably affect the evolution. It's goes on in such a quick time scale.
I was curious to know if anybody's doing any similar calculations without making the Polyakov
Can you
approximation.
speak louder, please? Pressure for everyone.
Sorry. I was curious to know. I was sitting right next to the microphone, so I guess I wasn't worried about it. I'm curious to know if anybody's doing calculations without the Polyakov approximation,
So
Is that-
calculations without
or even
Yes.
even made any inroads without it.
So the problem is that, well, exact 3.1-dimensional calculations are complicated first, and even without quantum effects, but with quantum effects even more so. And basically, with current techniques, the only space-times for which the normalized Chasson tensor can be accurately calculated are static ones. So basically, you take static black hole. There's calculations done for Schwarzschild horizon nostrum black holes, curved black holes even, but without any time evolution. So they're stationary. at
Okay.
least.
But you could maybe imagine following a strategy like the mathematicians, right? Where you say, okay, I'm not going to try and calculate it exactly, but I can try and prove something about it. Is that
Yes. So in fact, the flux we get at the inner horizon is something that has been calculated in 3+1 dimensions in the vicinity of the Cauchy horizon. So it's the same flux that, if taken to the just a very initial one, if you take this flux and you see what physically looks like in extended geometry and your back reaction all the way to the Cauchy horizon, then it's pretty much the same term that diverges, and that's been calculated in 3+1 dimensions. So you can use calculations in static and stationary spacetimes to support results in dynamical spacetimes in this approximation, but doing full calculations on dynamical backgrounds and even doing backreaction on top of that is something that's a bit beyond current techniques. But maybe.
Yeah, you'll get them. Thank you. Are there any more questions? All right, if not, then let's thank Valentin again. Thank you.
If you enjoyed the video, like and subscribe.